Alright, so in this video, we're going to start looking more at magnetic forces and what happens when charged particles move in magnetic fields and things of that nature. So in this case, I've drawn a magnetic field. The magnetic field is in green. And as you can see, it's directed into the screen or the page. That's what those X's mean. That's like looking at the tail feathers of an arrow. Now, in this magnetic field, I have a proton, not necessarily a proton, I have a positive charge that's moving to the right, okay? If it's moving to the right, let's think about the direction of the force on it. If I put my right hand and I point my fingers in the direction of the velocity, so here's my fingers, and I need to curl them into the board. That means I need to be able to bend them at my knuckles here, make a little fist. My thumb's going to point straight up. That tells me that the force is up on a positive charge. So this won't continue in a straight path to the right. We will in fact feel an upward force. Now, when it's right here, it actually has a velocity straight up. So what happens if the positive charge is moving up? Again, if I point my fingers of my right hand, here's my right hand, straight up, and I want to curl them into the board, so I'm going to be able to make my little fist here, I'm going to have my thumb pointing to the left. Because I have my right hand, you can put them in front of you. Fingers are straight up, but they have to be able to curl towards the board, which means my thumb is going to point to the left. So I know now F is left. That means that this particle is going to continue to move until it's moving directly to the left. At that point, when it's moving left, if I put my fingers of my right hand in the direction, I'm now going to have to do it with my pinky up here. There's my pinky finger. There's my four fingers. And I need to be able to curl them into the board. So I'm going to make my little fist. And my thumb will be pointing down. So now the force is down. So it'll keep right on moving. You can see here, when it's moving down, the velocity is down, the force will be back to the right. It will in fact move in a circle. We start off with a situation, let's think, where the initial velocity, in fact the velocity is always perpendicular to B. And of course that means that our force is always perpendicular to both of them. Anytime the force is perpendicular to velocity, it causes a change in direction, but it does not change the speed. Because the force is perpendicular to velocity, it only changes the direction, not the speed. When we have a force that causes something to move in a circle at a constant speed, that is a centripetal force. So we have a centripetal force, in this case, that's caused by a magnetic force. Remember, centripetal forces are always caused by something. They can be caused by the tension in a string. They can be caused by gravitational force. In this case, it's caused by magnetic force. Centripetal force is mv squared over r. The magnetic force in this case is just qvb. We usually put the absolute value. Now, if it's a positive charge, it's going to be positive, but what this gives us magnitude. Notice v cancels. One of the v's cancel. If I solve this for r, I can see that the radius is simply going to be mv over qb. And if we look at this, it makes sense. mv is momentum. The greater the momentum of the particle, whether it's because the particle is heavy or the particle is fast, the larger that radius is going to be. We would picture, if we were just thinking, that if we had a faster moving particle, this particle was moving faster, we would expect that it would make a bigger circle, simply because it was moving faster. Same thing if it was heavier, it would be harder to turn. Similarly, if the charge or the magnetic field are stronger, those will create a greater magnetic force. The stronger that magnetic force is, the tighter we expect that circle to be. So the numbers really make sense. Now, one of the places that we use this type of motion, and there's actually quite a few, they're used in things like cyclotrons, particle accelerators to keep things moving in a circle. But one application is a device called a mass spectrometer. You may have heard of a mass spectrometer. Oh, I'm in pretty purple. Mass spectrometers can be used to identify unknown particles by their mass, or often by their mass to charge ratio. They basically consist of two parts. We start with a velocity selector. Now, velocity selector has both an electric field and a magnetic field. We're going to put a little opening here. Those don't actually touch each other because we don't want to short out, but there is something. There we go. An opening up here that these particles are coming down. We'll assume for now they're positive. And there's another opening for them to go out. Now, our magnetic field, we're going to draw pointing coming out of the screen. The dot means the magnetic field points out of the screen. That's the tip of the arrow. So B is out of screen. The X's were into the screen, the little dots are out. Now let's think. If we have the magnetic field pointing out, if we use our right hand, if I point my fingers straight down and I curl them where they're going to curl out, I can see that FB is going to be to the left. So these particles are going to feel a magnetic force that way. I want to balance that with an electric force. So I'm going to make this side positive and this negative. And that's going to tell us that then we've got an electric force to the right. So magnetic force, electric force, when they're balanced, this gives us that QVB, that's my magnetic, has to equal QE, that's my electric. And the velocity of the particles is going to be given by the ratio of the electric field magnitude to the magnetic field magnitude. This does have units of meters per second. Okay, so the first part of our mass spectrometer is simply our velocity selector. Now when they come out, let's draw some more particles. Here they go. They're going to come. They're going to continue into another region where the magnetic field is pointing out of the board, the larger region. Only now we no longer have that electric field. So we don't have the electric field that's exerting a force to the right. We only have the magnetic field, which is exerting the force to the left. So when the particles come out, right here we're going to have a photographic plate that's going to help us detect where the particles are hit. And when they come out, they're going to move in a circle. In fact, this will be the diameter of the circle from here to here. That distance right here is the diameter. Now, if you have particles that have different masses, you may have some particles that have a different diameter. So where those strike is what's important. Let's look at an example. Suppose we have a mass spectrometer. It's got a magnetic field of 1 times 10 to the negative 3 Tesla. Our particles that we put in there have a speed of 5 times 10 to the third meters per second. And each of our singly ionized particles, so we're going to have positive ions, is going to have a charge of 1.6 times 1.60 times 10 to the negative 19 coulombs. In other words, they've simply lost one of their electrons. All right, let's see if we can find that radius for the different carbon isotopes. Remember, an isotope is an atom that might have a different number of neutrons in the nucleus. They have the same atomic number. For carbon, the atomic number is 6. So they all have 6 protons. But carbon-12 has 6 protons and 6 neutrons, and it has a mass of 1.99 times 10 to the negative 26 kilograms. Carbon-13 has a mass of 2.16 times 10 to the negative 26 kilograms. And carbon-14, which is the one that you hear about when they talk about carbon dating, where they carbon date fossils and things, because carbon-14 is actually radioactive with a very long half-life. It has a mass of 2.32 times 10 to the negative 26 kilograms. So to get our radius, we just use the formula mv over qb. So for carbon-12, we would put in the mass of 1.99 times 10 to the negative 26. It has a speed of 5 times 10 to the negative 3. 5 times 10 to the positive 3. The charge is 1.60 times 10 to the negative 19. And our magnetic field, 100 times 10 to the negative 3. And we found out that for carbon-12, this radius is 0.62 meters. If you wanted the whole diameter, you would have to double that, be 1.24 meters. So it would come out way over here. This would have to be a fairly large piece of equipment. If we do the same thing for carbon-13, it comes out to be 0.68 meters. And if we put it in for carbon-14, let me work this one real fast. 2.32, whoops, 2.32 times 10 to the negative 26 times 5 times 10 to the third divided by 1.6 times 10 to the negative 19, and then divided by 1 times 10 to the negative 3. And that came out to be about 0.73 meters. So they would all land slightly different places. If we double those, that's going to be about 1.36 meters. And this one will have a diameter of about 1.46 meters. So that's a mass spectrometer and how they work. All right, the rest of today's is probably going to deal with forces on different types of, well, really just forces on wires. What happens when instead of having just a single charge, we now have a continuous current? Because up till now, we've looked at magnetic forces acting on isolated charges. So let's look at magnetic forces on a current carrying wire. So now instead of having just individual charges, now the only difference is our charges are confined within a wire. We already know for individual charges that force is absolute value of Q, V, B, sine phi, where phi is the angle between the velocity vector and the magnetic field vector. Notice if we look at this, the units for charge are coulombs, and the unit for speed is meters per second. A coulomb per second is a current. If I just think about this, I'm not going to really prove my formula, but it makes sense. That is current. So this basically turns into the current times the length of the wire times V times sine phi. That's the force on a current carrying wire. I, of course, is your current. It's going to be measured in amps. L is the length of the wire. The longer the wire, the more force. And of course, B is your magnetic field strength. And phi is now the angle between the current and the magnetic field. The direction of the current is the direction of the velocity, so it's really the same rule. Instead of us having a single charge maybe flowing to the north, we might now have an entire current flowing to the north. We use the same right-hand rule. What do we do? Instead of saying fingers in direction of V, that also is the direction of I. So if you have a current, fingers in the direction of I. If it's a single charge, we think of fingers in the direction of V. If necessary, rotate your hand, but you need to be able to curl your fingers from the current, whether that's V or I, to the direction of the magnetic field. Your thumb will give you the direction of the force. On conventional, which is positive charge, conventional current, or positive charge. So, same right-hand rule. So that's really nice. Let's look at an example. Our first example involves something called a magnetic railgun. And a magnetic railgun consists of two plates. One of them is going to be positively charged and one of them is going to be negatively charged. We've seen that more than once. We're going to have a magnetic field that's going to point directly into our screen. And we're going to have a conducting rod, a piece of metal. This is conducting plate, so we've got two conducting plates. And I'm going to lay a rod on top of this. And when I do, if these plates are charged, and we're going to decide which plate should be positive or which plate should be negative in just a minute, I wanted to feel a force this way. Magnetic railguns are actually used to launch things. And if the force is strong enough, this conducting rod that I just drew will go flying off this gun like that. But I need a force on it. If I want the force to be to the right, let's think about this. We're going to connect a battery. And the only question that we have to decide is, do we want the battery like this? Or do we want the battery like this? Okay, when I connect the battery, whichever way I connect it, whether I do this or whether I use the other one, it's going to cause these plates to become charged. And when it does, current's going to either flow down or flow up. Think about which direction I need the current to flow. I need my fingers to point, to be able to curl into the board. I need my thumb to point right. That tells me I want the current to go down. If the current is going down and I curl into the board, the force on that metal rod, that conductor, is going to be to the right. If I want the current to go down, then I have it connected correctly. This plate's going to be positively charged, and this plate will be negatively charged. That's going to cause current to flow down. The downward current is going to cause a force to the right, and that's going to be how it works. These are called the conducting rails. The question just wanted to know which way to connect the battery. This will be the correct way. Let's do one more. This is number 29 from the back of the book. It says a magnetic field is used to suspend a wire. So we have a wire. It has a mass of 0.02 kilograms, and it has a length of 0.15 meters, and it's carrying a current of 10 amps. Better put another 0 here. I want 2 significant digits. It says, what is the minimum magnetic field needed to balance the pull of gravity? So here's this little wire. It's got 10 amps of current going through it. I know that gravity is going to try to pull it to the ground with a force mg. I want to create a magnetic force that opposes this. That will be equal to ILB. Now, let's stop and think. If the current is to the right and I want the force to be up, so my fingers have to go right, my thumb has to go up, I can see that I need that magnetic field to point into the screen or into the page, whichever way you're thinking. If the magnetic field points into the screen and the charges are traveling to the right, then they will feel an upward force. Okay. The minimum magnetic field needed will be, of course, when everything's at right angles, so I don't have to have a sine phi, which will kind of reduce things. So I just want that magnetic force to balance gravity. When will ILB equal mg? If I solve that for B, I get mg over IL. That's 0.020 kilograms, 9.80. The current was 10 amps, and L was 0.15 meters. It just comes out to be 0.13 Tesla. All right, we're going to do one more lesson in this video. And we are moving into section 20.6, and it deals with force and torque on a current loop. Let's start off with a magnetic field pointing straight down. Here's a uniform magnetic field, point straight down. In that magnetic field, we're going to put a rectangular piece of wire. Put some leads on it over here and over here. These are some type of support. These can be not conductors. These are not leads. Suppose that I'm going to call this point A, B, C, and D. I'm going to call this the length. And from here to here, the width. So I have a rectangular area, length times width. The current is going this way. And here it's going this way. It's in a loop. This way and this way. I'm going to change the color here. These are not, erase that black. This is not part of the wire. I don't want you to think that's part of the wire. Those are just some type of little handles sticking out because we want to think about the possibility of maybe these are on some type of support for the purposes of being able to spin in a minute. All right. We know the force on a wire is I, L, B, sine phi. If the current is in the direction of the magnetic field, there's not going to be any force. So I can tell you right now, the force on section AB is 0 because the current is parallel, the current's coming straight down to the magnetic field. I can tell you that the force on section CD, also 0 for the same reason. Even though it's at 180 degrees, sine of 180 is still 0. However, we are going to get a real force if we look at AD. That's the piece across the top that I drew. The current's going to the right. If I put my fingers, my right hand, the current's going to the left up at the top section. Take my right hand, rotate down. I can see that that one wants to come, the force is out of the screen. So this top segment wants to rotate. If you think of the square being free to rotate, it would like to come out of the screen. If I look at the bottom segment, put my fingers in the direction of the current, and I rotate down, my thumb points in. It wants to go in to the screen. So this whole thing wants to rotate. It would like to rotate until the magnetic field lines would actually be going through the hole in the middle, which is what it likes. The loop will rotate after we've looked at this. The loop will rotate until a normal with the line, let's say a normal with the plane of the loop points in the direction of the magnetic field. If you could picture a handle right here in the middle that sticks straight up, I can't draw it sticking straight up because it's perpendicular. But if you picture right where I put that dot, a handle or just a straight line normal sticking, it will want to rotate until that thing points straight down. And after it rotates, it would look like this. Just redraw, here's our it wants to rotate until that normal segment that was, instead of sticking straight out at us, is in the same direction as that magnetic field. That's what it would like to do. Here's our two little handles so that we kind of drew sitting there with some kind of thing where they're free to rotate. That's what it would like to do. This position would be considered stable equilibrium. If it can rotate until that normal till this side up at the top that wants to come out of the screen, and then the segment at the bottom, BC, wants to go into the screen, it will stay. If it rotated the other way, where the normal pointed up, like this, that's actually still equilibrium, but that's unstable equilibrium. Because if you touch it the least little bit, it will try and flip around until its normal aligns itself. Okay, so this brings up the idea, okay, so how much force? Let's go back and get a formula for torque. I'm going to kind of redraw my picture. Here's my magnetic field. Here's my loop. It's got a width, it's got a length, and it's got current. Here's the current going this way. Here's the current going this way. And here's the axis of rotation. It's going to rotate around this line. There's the two little pivot points. Now, if we think about it, we know that torque equals force times the lever arm. In this case, the lever arm is this distance from here to here. So our force is ILB sine phi. Our lever arm is 1/2 the width. Now, that's the torque on the upper piece. If we add the torque on the lower piece, it looks exactly the same. Now, let's do a little reorganization. 1/2 plus 1/2 is 1/2. So those two, if I add them together, I actually get something that looks like IL, and I'm going to move this W right here, B sine phi. But this is simply the area of the loop, which turns it into IAB sine phi. What is phi? That's really important. It's the angle between the normal to the plane or to that loop and B. Some people will say it's the angle between the area vector and B. You can kind of think it's that normal to this loop, this imaginary vector that's sticking out, that normal as kind of representing the, quote, direction of the area. Area is not really a vector quantity, but that normal to it does have a direction. If you did this same thing and you, well, I'll tell you what, let's carry on. This little part right here, IAB, not IAB, my mistake. This little part right here, IA, gets a special name. It's called the magnetic moment. Obviously, the larger it is, the more torque you're going to have. And it's represented with the symbol of a mu, and it's equal to I times A. The units are simply amps times meters squared, so don't get caught up in anything fancy. So that's our formula for finding the torque. Now, we did it with a rectangular loop, but this is also true for circular loops, and honestly, most of the time they are circular loops. If you have multiple loops, suppose we have something circular and we'll have a bunch of loops. Let's let the normal stick straight out. We're going to let the current go this way. If it's in that same uniform magnetic field that points straight down, it has the same torque. In fact, if it was being supported and it was free to rotate, its torque would be given by N times I, A, B sine phi. The only difference between this and this is that N is the number of loops, which are also often called the number of turns, because when you're wrapping things, you can count how many turns you have. It has its magnetic moment would just be N I A. So if we have multiple loops, the only difference in our formula is we have to multiply by the number of loops, because each loop feels that much torque. So that makes sense. If there's a certain amount of torque for one loop, if you have 100 loops, you're going to have 100 times the torque. This may not seem terribly important, but this is actually the interior of almost every electric motor. Every electric motor basically consists of a coil of wire inside a magnetic field. And that magnetic field exerts forces on that coil that want to make it rotate. Now, normally you would think it would rotate and stop, but we'll talk about why it doesn't here in just a minute. Let's do an example. We have a circular coil . It has a radius of 0.0500 meters, so we have 3 sig figs. It's got N equal 30, so that's the number of turns. It lies in a horizontal plane. It also has a current going through it of 5 amps counterclockwise when viewed from above. Okay, so it's lying in a horizontal plane. B is equal to 1.20 Tesla directed to the right. So if we look at this, let's make a view from above. So we're looking down on top of it. From above, here's our circular coil. It's got 30 turns. I don't need to draw 30 turns, but we get the gist. We've got current going counterclockwise. And there is a magnetic field that is directed to the right. It says find the magnetic moment, mu, and torque, and then find it which way it wants to rotate. So mu is just N, I, A. So we have 30 turns. Notice that is exact, so we don't have to worry about sig figs on turns. They tell us exactly how many turns. We have 5 amps. We have an area that is pi r squared. So mu is 1.18 meters squared. Our torque, of course, is just N-I-A B sine phi. Well, we've already calculated this part. So 1.18 times 1.20. Our angle is 90 degrees, right? Picture that normal pointing straight at us. It's at a 90-degree angle with the magnetic field. And we see that the torque is 1.41 Newton meters. So that's the torque. That's the magnetic moment. The only thing left to question is which way does it want to rotate? It wants to rotate until that normal points in the direction of the magnetic field. I don't know the best way to say that, but this side, where the current's going up, picture that current going straight up, fingers up, curling to this way. This wants to go into the board, the left-hand side, the right-hand side. Over here, the current is down. This wants to come out of the board. Okay, the whole thing wants to rotate until this normal that's pointing straight at us is aligned with that magnetic field that points to the right. All right, why are these so important? Well, in other years when we were doing labs face-to-face, we would probably actually build an electric motor. But these are the heart and soul of DC motors. Let's set a situation where I have a magnetic field that points to the left here. That's called the field. Usually we have a field magnet, but this is our magnetic field. We take a loop and it's going to have a bunch of windings or turns. Okay, now we do it in such a way that we keep reversing the current. So we take some little brushes. Instead of being wired solid to it, we just touch it. And we connect those to our battery. And current's going to flow this way. And it's going to be going in here. So here's our current. If I put my current going in the way I've drawn it, it's going to want to make this rotate. Well, this is going up and out. This side will want to come out, and this side's going to want to go in. But when it reverses and it flips 180 degrees, these brushes change sides. In other words, this was the side with current going in, and it's going to be the side with current going out. It reverses the current so that instead of being in a state of stable equilibrium, it's actually in a state of unstable equilibrium, and its momentum will cause it to rotate again. Every time it thinks it gets to stable equilibrium, these brushes flip sides, and it's an unstable equilibrium, and its inertia essentially just keeps it moving and moving and moving. This coil inside is called the armature. These are called brushes. They touch the leads, but they're not wired to the leads. So as it rotates, there'll be a split moment where it won't be touching either brush, but it will keep rotating and it'll keep reversing its current every 180 degrees. Okay, this is where we're going to stop. I know that was a lot to take in. So I will see you or talk to you in our next video.